Today we're going to talk about MOSFET current voltage characteristics. So let's say that we have a bar of semiconductor material. Like so. And there is some current I flowing through the bar in this direction. If the charge density along the direction of the current flow is QD, measured in coulombs per meter, and the velocity at which the charge moves is V meters per second, then the current seen passing through the bar is simply that linear charge density multiplied by the charge velocity. Okay. So let's now consider an NMOS transistor. Like so. I'm going to try to draw the picture of kind of the surface of one here. So we have our N plus source region. Over here, we'll have an N plus drain region. Over here, we'll have our P plus body connection. And here, all right. So I'm going to try to extend this drawing into 3 dimensions if I can. So this is our gate. And then this is the profile of our active region that's going to form our drain. Similarly, this is a profile of the active region that forms our source. And our body connection will be something like this. And let's assume that our body terminal is at ground so that we don't have any body effects to worry about. Our source terminal is also at ground. Our drain terminal is at ground. Our gate terminal is at a voltage of VG exactly equal to the threshold voltage. So what should we expect to occur? What is the definition of the threshold voltage, right? So if VG is at the threshold voltage, we have strong inversion, which means a channel has formed. So we have a bunch of electrons all kind of tucked down here below the gate. Does current flow? What was that, Taylor? Why? Right, but if there's no potential difference, what's pushing the charge in one direction or the other? right? So this is how a field effect transistor works, right? So the applied electric field on this gate portion pulls those electrons into the channel, but if we don't have a potential difference, we don't drive the current in one direction or the other, right? So since the onset of inversion occurs at VGS is equal to VTH, the inversion charge density produced by the gate oxide capacitance must be proportional to VGS minus VTH. Okay. Or let me write this down. Since the onset inversion occurs at VG is equal to VTH, the inversion charge density produced by the gate oxide capacitance, Cox prime, must be proportional to the quantity VGS minus VTH. So effectively, what that sentence says is that when we apply a voltage to the gate, positive charge is accumulating on the gate, and that same amount of charge needs to be mirrored in the channel, right? So for however much positive charge we have in the gate, we get the exact same amount of negative charge in the channel. So for VGS greater than VTH, any charge placed on the gate must be mirrored in the channel. So what we'll see is that for our MOSFET device, we will have a linear charge density QD that is dependent on the width of our active regions multiplied by our gate oxide capacitance, and then multiplied by the quantity VGS minus VTH. So we're effectively saying that the distribution of charge present in the channel depends on the physical parameters of the MOSFET, the oxide capacitance, and then our voltage applied, right? So it's the area or a portion of the area, since this is charge per unit length, oxide capacitance, and applied voltage. So what would happen? Take this same picture. Now, we apply a voltage. My pen thing will erase. At our drain terminal, where VD is greater than 0 volts. So what do you think is going to happen? Any thoughts? So current will flow. Yeah, but what's that going to look like internal to the MOSFET? So let's take it to an extreme here. I mean, so if we apply a non-zero voltage, there's going to be a difference in the electric potential across the channel, right? So on the source side, the potential difference is VG minus 0. And on the drain side, the potential difference is VG minus VD, right? Where VD is greater than 0. So we're going to see a large potential on the source side and a smaller potential on the drain side. So our distribution of charge is no longer going to be evenly spread across that region, right? So we're going to see something that looks more like this, where it's kind of tapered. All right. And the reason for that, again, is because the potential difference between the gate and the source is larger than the potential difference between the gate and the drain region. So if we consider this point to be 0, and let me draw this line straighter. This point to be the effective length, and a point here in the middle just represents some displacement along the gate. We could say that our linear charge distribution as a function of position is now going to look like W effective times Cox times VGS minus the potential at location X minus our threshold voltage. Now going back to, I think it was what Mr. Pozniak said, now that we have that potential difference between our drain and our source, we should see some current flow. So what should the current flow be? Well, it's just this linear charge density multiplied by the velocity, right? Because we're just treating this thing like the bar we talked about at the beginning of class. Our drain current, oops, sorry. ID is going to be negative W effective Cox VGS minus V as a function of X minus VTH times carrier velocity V. And understanding that for a semiconductor, carrier velocity is simply the product of the mobility and the applied electric field, and the applied electric field is simply the derivative of the voltage with respect to position we find that our drain current ID is equal to our effective width times our oxide capacitance times VGS minus V of X minus VTH multiplied by mu N, because we're dealing with an NMOS transistor here, so we're going to be dealing with the electron mobility. dV by dx. So we're going to rearrange this guy slightly, okay? Going to get rid of some of this crap. If I integrate ID with respect to dx from one side of the channel to the opposite side of the channel, this will be equal to the integral from v is equal to 0 to v is equal to v ds of mu n C ox W effective times VGS minus my potential as a function of position minus VTH dV. Okay. Performing this integration, and then dividing both sides by the effective length. Okay, here. So like ID, my drain current, does it depend on position? Let's think about this. Is there ever any element that you've ever dealt with where the current flowing through it changed as a function of position within the element? No, because to do so would violate the law of conservation of charge, right? So we could take ID outside, and when we take the integral from 0 to 0 to L effective for the position, that's just really multiplying the drain current by the length of the channel, right? So I'm going to move that L effective to the other side of the equal sign by dividing both sides by that. So what this is going to give me mathematically is going to be ID is equal to mu n C ox W effective over L effective times VGS minus VTH times VDS minus 1/2 VDS squared. And this is valid only for VDS less than VGS minus VTH. So we have this VGS minus VTH. So we effectively are integrating this constant term, which is where from 0 to VDS, where this guy comes from. And then when we integrate this voltage, so the integral of V dV is going to give us this 1/2 VDS squared bit here. Okay. So if we were to plot our drain current ID as a function of VDS what we would observe is a set of curves that look something like this. I'm trying to draw these as least crappily as I can. Those colors are too close together. Where for voltage VGS1, VH, this guy occurs for VGS2 minus VTH, and this guy occurs for VGS3 minus VTH, where our gate source potential difference, so effectively our gate voltage, is just getting larger and larger in each instance. Okay. What is interesting about these guys is that they follow a simple parabolic relationship. That doesn't look particularly parabolic, but this guy right here, we'll call ID max, is going to be equal to 1/2 UN Cox W effective over L effective times the quantity of VGS minus VTH squared. So what can we glean from this graph? Well, ID increases as the quantity VGS minus VTH increases. This guy right here may be commonly referred to as VOD, which stands for the overdrive voltage. It's the overdrive voltage because it's the voltage greater than what you need to just turn the transistor on by establishing the channel. Okay. So when, VDS is less than or equal to VGS minus VTH, we say that the transistor operates in the triode region. This nomenclature comes from what was used for vacuum tube based transistors. So I honestly don't know what triode really means, because this isn't 1955. All right. So when VDS is much less than twice VGS minus VTH, we say that the transistor is operating in the deep triode region. So what I'm talking about there is this region. So in this region, our current is increasing very close to linearly. And so we can simplify our drain current expression to be mu n C ox W effective over L effective times VGS minus VTH times VDS, right? So when VDS is very, very small, you square it, it gets even smaller, and that part effectively gets thrown away from our original expression. So we have a roughly linear relationship between our drain current and our drain source voltage. Okay. Since we have a linear relationship between current and voltage, what is the transistor behaving like? As a question. Pardon? A resistor, yeah. Where we could say that that resistance R, I have in my notes here, I think it says R on, so I'll just write R on, is 1 divided by UN C ox W effective over L effective times VS minus VTH. So from this, we can see that a MOSFET may act as a voltage controlled resistor. And again, VDS is much, much less than VGS minus VTH. Why do you think, like what would a practical use for a voltage controlled resistor be? So in short, is generating bias circuitry, right? Where we need very, very precise levels of voltage to cause transistors to turn on. So we actually use transistors as resistors in those schemes because we have a better control of what the resistor value will be, right? So we could use a voltage divider circuit or something like that, which is relatively infallible to process variations because it's all based on the ratio, to transform our 5-volt supply or our 3.3-volt supply or something like that. We can scale it down into a much smaller voltage to create a very, very specific and exact resistor value in our biasing circuits to make them behave the way that we want to, right? So typically speaking, some of the resistors in our biasing circuits, and I'm trying to remember off the top of my head which ones in 336 didn't wind up getting biased with a simple voltage divider circuit. We use a voltage divider to apply a specific voltage to a transistor to make a specific gate source voltage to a transistor to make it behave exactly like a particular resistor value. And it occupies significantly less space than an actual resistor as well. All right, so let's revisit this picture. what happens to our profile here? I can erase all this crap. When VD, so actually let me change this. This will be VG greater than VTH, and VD is greater than VG. So we're beyond the threshold voltage, so our transistor is well and on. We have some overdrive voltage present. And now we have turned our drain voltage up higher than that level of biasing. And I can actually call this greater than, or I'll leave it as greater than. Actually. What's going to happen to the charge density profile? So when ED was non-zero, we saw that it began to tilt, right? It was perfectly level, and then it began to tilt. The higher that we raise VD, the more that profile is going to tilt. So for a large value of VD, we might see something like this. That's drawing straight lines on this thing. So we got all of our electrons and all that kind of stuff buried in here. If you recall, this is our 0 point. This is our effective length of our channel. I'm going to call this guy right here L electric, L-E-L-E-C, okay? And this phenomenon here, where the channel winds up not extending for the entire length of the physical channel area, is called pinch off. Okay. So effectively what's happening is that the charge density is dropping to 0 for some length X is less than L effective, right? And so that's occurring because VD is at a greater potential than VG. So we shouldn't see any electrons stored over near the drain because it's at an even higher potential than the gate is. Right? So if we revisit our device current integral, where we had starting at X is equal to 0 and going to, let's see, I have this integral going to L prime. I want to make sure that I remember what exactly L prime, I think that's just to L electric, really. Yep, that's exactly right. Need to be more consistent in my notes. ID dx, our integral here is from 0 to VGS minus VTH, where we're under the assumption now that VDS is greater than VGS minus VTH. We're going to have mun Cox W effective multiplied by VGS minus Vx minus VTH dV. And so this yields ID is equal to 1/2 mun Cox W effective over L electric VGS minus VTH quantity squared. Again, for VDS is greater than or equal to VGS minus VTH, where this region of operation is known as the saturation region. Okay. So what the saturation region means, and this is generally what saturation means in electrical engineering, is that an increase in the input voltage, VD in this case, does not cause a corresponding increase in the output signal, which in this case is the drain current ID, right? So this equation here is completely independent of VDS other than this constraint that VDS be larger than our overdrive voltage. Okay, so the more and more and more we jack up that voltage VD beyond what our overdrive voltage is, it has no effect on our output characteristic whatsoever until we talk about channel length modulation, which will be the next thing, right? So since we have a very, very stable amount of current flowing out of this MOSFET, what could we use the transistor as when it's operating in the saturation region? Current source, exactly right. Okay. And it behaves source because the amount of current is independent of the voltage drop across its terminals. So meaning that you can have a very, very large drain source voltage and the current is very, very stable. It's not going to fluctuate too much. So now let's talk about channel length modulation. And then I think this will wrap us up for the day. And we'll get into some operational modes we're less familiar with for the next class meeting. Okay. Channel length modulation. All right. So I know that I literally just said that the drain current is largely independent of the drain source or the voltage applied at the drain when it exceeds the overdrive voltage, right? But what's physically happening in the device when VD is getting larger than VGS minus VTH? Let me go back to this drawing here, all right? So if VGS were exactly equal to the if VDS were exactly equal to the overdrive voltage, pinch off would occur right here. As that VD gets larger and larger and larger, the location of where pinch off occurs makes the channel shorter and shorter and shorter, right? The actual length of the channel that's supporting that charge density gets shorter and shorter and shorter. And so we should see that as this L electric gets smaller and smaller and smaller, what should happen to the drain current? It should actually go up a little bit, okay? So this phenomenon is what's known as channel length modulation, okay? So since the position along the channel where pinch off occurs is dependent on our voltage VDS. Device current is not truly constant in saturation region operation. Instead, the device current depends on a channel length modulation coefficient. And I'm going to use capital lambda for this. So in 335 and 336, we used lowercase lambda, but lowercase lambda in this class is our scaling factor for our size. And so I can't use the same signal or same symbol for both things, or that'll be wildly confusing. So I am electing to use capital lambda, where our drain current now is 1/2 UN Cox W effective over L effective VGS minus VTH squared. And then we have this extra term of 1 plus lambda VDS minus, our textbook uses the quantity VDS minus VDS saturation. Some other textbooks throw away this term right here because it's typically a pretty small voltage. So this guy is usually on the order of 1/4 of a volt-ish. It just makes our function more continuous looking, so there's not an abrupt shift in the current level, okay? So what does this parameter lambda represent? All right, so lambda represents the relative variation in length for a given VDS value. So what that means is that if we have a very long channel device, lambda is going to be small because an incremental change in VDS is going to cause a very, very small change in the effective channel length. But if we have a very short channel device, a small change in VDS represents a large change in the pinch-off location, right? So the smaller, or the larger we make our transistors, or the larger channel length we make our transistors, the smaller the effects of channel length modulation will be. So if we need to use a transistor as a current source, we want to make it with the correct aspect ratio to give us our current, but we want to make sure that so like just because it's a 10/2 from our specs, because that width over length ratio works, if we wanted to minimize the effects of channel length modulation, we might make it 100/5, or no, 100 yeah. No, that's not right. That'd be 25/5. Why can't I do 100/20? Sorry. Multiplying by 10 is apparently beyond me. That's terrifying. I apologize for my shitty math today. So anyway, we can make the transistor physically larger to minimize those effects of channel length modulation and give us a nice and stable current source. And then as you all know, we can do other tricks like cascoding and all that kind of stuff, which we're going to review to also increase stability and all that kind of good stuff. All right. I think that's enough out of me for today.